Let's look at factoring the difference of two squares. This first problem is called the difference of two squares because you have a square minus a square. And 49 can be thought of as 7 squared. And this is going to factor into x plus 7 times x minus 7. And again, we've taught this before, these two expressions are known as conjugates of each other. Basically, they are a plus b and a minus b. And let's check this by FOIL. If you do the first part of FOIL, x times x, you get x squared, and that works. If you check your outer and your inner, you have a minus 7x and a plus 7x, and those are going to cancel each other out. Then you have the L part of FOIL, 7 times negative 7, which makes negative 49. And so anytime you're multiplying conjugates, these two middle terms are going to cancel each other out. And so instead of factoring the whole FOIL, you're just looking at the F and the L. And make sure you have opposite signs. Now that allows us to really speed things up once we notice this pattern. X squared minus 64. We notice that 64 is a square, and we can have x plus 8 times x minus 8. And for the next problem, x squared minus 25, that becomes x plus 5 times x minus 5. Now, when you get to a problem like number 4, you go, uh-oh, this is not a perfect square. You could force this by going x plus the square root of 10 and x minus the square root of 10, but it depends upon the directions. Usually you're factoring over the integers, and we would just leave this as prime. But I'm just going to make a note here. This will be the way we're going to factor this in college algebra. But for this class, and it depends upon your teacher and your system, whether you're going to be using square roots when you do your factoring. When you have fractions, don't let that scare you. You square root the numerator and denominator separately, and so we will have x plus 1/6 and x minus 1/6 accordingly. The two middle terms of FOIL cancel each other out. Now, when you have the sum of two squares, that's something that you want to be careful of, because that will not factor using real numbers, and so we would just use the word prime here until we learn about imaginary numbers, at which point that will be factorable. But for now, this is not factorable. We can factor the difference of two squares, but not the sum of two squares. If your expression that you're solving has more than one variable, don't let that scare you. You have the square of both x and y at the beginning here, so this will give us xy at the beginning of each parentheses, and one parentheses will get a plus 10z, and the other will get a minus 10z. And if you multiply that together, it's going to work. When you have higher powers, don't let that scare you. This x to the fourth is really x squared squared. So when we apply this procedure, we're going to have x squared plus 4 times x squared minus 4. But we don't stop there. Notice that the x squared minus 4 is itself a difference of two squares. So we leave the x squared plus 4 as it is, because the sum of squares does not factor, and the difference of squares will factor into x plus 2 times x minus 2. When the exponents get much larger, still don't let it scare you. These are both even exponents, and we can factor this into x to the fourth plus y to the fourth times x to the fourth minus y to the fourth. Now the sum of two fourth powers will not factor, but the difference of two fourth powers will. We're going to keep the x to the fourth plus y to the fourth as it is, and the difference of these two fourth powers will become x squared plus y squared times x squared minus y squared. Now these first two groupings will not change, but this last one is the difference of two squares and will factor further. So our final factored form will be x to the fourth plus y to the fourth times x squared plus y squared times x plus y times x minus y. Okay, I know that's a lot of work, but it's really the same process being repeated over and over again. For number 10, the numbers are rather easy. We just have x plus 1 times x minus 1. For number 11, 5x plus 4 times 5x minus 4. A plain old difference of two squares, no trick involved. In number 12, again, square root the 100 to a 10x, square root the 49 to a plus 7y, and then multiply by the conjugate 10x minus 7y. Now, in number 13, we tend to make mistakes. What tends to happen is people say, the answer is going to be 5x plus 10 and 5x minus 10. But take a closer look. Notice how there's a common factor in each parenthesis that could have been divided out. You can save yourself a lot of time by going back to the original problem and asking, can I take out a GCF? And the answer is yes. 25 divides out, and we're left with x squared minus 4. Then we've got the difference of two squares that'll break down, and we've got 25 times x plus 2 times x minus 2. Now you can salvage that first line I've crossed off, but it's a little bit tricky because people would have to factor a 5 out and have x plus 2 in the first grouping, factor a 5 out, have x minus 2 in the second grouping, and then put those 5's back together to make that 25 there. And most people, once they get to this line that I've crossed off, don't usually look any further. So moral of the story is you want to always look for a GCF that can be factored out as step number 1 of the factoring process. Number 14 contains 4 terms, and usually that's the clue for the grouping method. And if I were to split this right down the middle as we normally do, I'd have an x which is common to the first 2 terms, and I'd have an x minus 6y left over. But notice there's no x minus 6y at the right. Also notice that this xy term kind of groups the first and third term together. So rather than being a 2-2 split, this is going to be a 3-1 split. I can factor the first 2 terms into x minus 3y times x minus 3y and then have minus 16. But that's really not the answer to a factoring problem because a factoring problem can't contain subtraction. But if I rewrite this as x minus 3y quantity squared minus 16, now I've got the difference of two squares again. Basically my pattern here is I've got blob squared minus 16, and that factors into blob plus 4 times blob minus 4. Well, let's use that same thought process and just substitute that x minus 3y for the blob. We will have x minus 3y plus 4 and x minus 3y minus 4. And if you want to do all the distribution and verify you get back to this top line, you're welcome to do so.